Good morning. Now, this is the next session of our module 1, which is first law of thermodynamics. Now, here we will learn about internal energy, a few definitions to molecular motion and molecular configuration. Now, internal energy due to molecular motion is called internal kinetic energy, and the internal energy due to molecular configuration is called internal potential energy. So internal kinetic energy plus internal potential energy can be together called by the name internal energy, denoted by capital letter U. Now, what is heat and work? Heat is actually energy transfer to or from a thermodynamic system. Then such mechanisms include conduction through direct contact of immobile bodies or through wall or barrier that is impermeable to matter, or any radiation between separated bodies. So when there is a suitable path between two systems with a different temperature, definitely heat flow occurs from hot body to cold body. Now, in thermodynamics, work is defined as mechanisms that act macroscopically and directly on the system's whole state variables. For example, change of a system's volume, that is through a piston's motion with externally measurable force, or change of a system's internal electric polarization through an electrically measurable change in electric field. All these are some mechanisms that can be called as work in the case of thermodynamics. So, like thermodynamic work, heat transfer is a process that involves more than one system, that is not a single system. In thermodynamics, energy is transferred as heat. That is in the form of heat. Then we can see work are of two types, in external work and internal work. Now, work done by the system on the surroundings is called external work. For example, consider a gas enclosed in a cylinder fitted with a piston. So suppose that the gas expands, then naturally the piston will move up. Here, work is done by the system, that is, work is done by the gas on the surrounding. Here the surrounding is the piston. So when work is done by the system on the surrounding, we call it as the external work. Here work is done by the gas on the piston. So this is external work. Now internal work means when it is nothing but work done by one part of the system on another part of the same system. That is, when the gas expands, the molecules will move apart. Okay, for this the molecules definitely has to do work against the intermolecular force of attraction, then only the gas will expand. So here work is done by the gas on itself, or work is done by one part of the system on another part of the same system. Okay, here the molecules are doing work on each other. So this is called internal work. So study the difference between internal work and external work. Now there is a mathematical notation. Suppose that the gas expands and the piston is moving up. Let it move through a distance dx. Then work done. We know work done is actually force into distance. Here the small amount of work done is denoted by dw. So that will be f dx, where dx is a small distance moved by the piston. Now this force is actually pressure into area, that is PA. dx is kept as such. Okay. Now pressure. So A dx can be replaced by dV, that is a change in or the increase in volume. So P dV. So dW, or work done, dW is equal to P dV. Okay. Now suppose that there is a change in volume from V1 to V2, then total, in order to understand the total work done, we have to integrate from initial volume V1 to the final volume V2. So total work done W will be equal to integral V1 from V2 P dV. Now what is first law of thermodynamics? This is very important. It is a restatement of principle of conservation of energy applied to heat energy. Now, you will be asked to state first law of thermodynamics, and you will be asked to write its mathematical representation. Okay, so first law of thermodynamics states that when some quantity of heat, that is dq, is applied to a system capable of doing work, then the heat absorbed by the system is partly used for increasing the internal energy du of the system and partly for doing work. So when you are dw, that is, so when you are supplying heat, a small amount of heat, say dq, to a system, then that heat that we are supplying to the system will be used by the system for two things. One is to uh, increase the internal energy by du, and the second part is to do some work dw. Okay, so dq is equal to du plus dw is the differential form of first law of thermodynamics. So when heat is applied to the system, dq is taken as positive by the gas. Okay, so dw will be positive. Now when gas is compressed, actually work is done on the gas. In that case, dw will be negative. Now when temperature of the gas increases, what happens to internal energy? Internal energy will increase, and du in that case will be considered to be positive. Now what happens when temperature decreases? Internal energy will decrease and du will be, or the change in internal energy, that is du, will be negative. So out of these three quantities, dq and dw, we know they are dependent on the path of the system, whereas du, or the change in internal energy, depends only on the initial and final state of the system and not on the path followed by the system. Okay, now we have already seen in the last class that zeroth law introduces the concept of temperature, whereas first law introduces the concept of internal energy. So this is very, very important. First law of thermodynamics. Now heat capacity. Heat capacity is also called as thermal capacity. It is a physical property of matter defined as the amount of heat to be supplied to a given mass of material to produce a unit change in its temperature. That is the definition for heat capacity. Its unit is joule per Kelvin. Now when you divide that heat capacity by the amount of substance in moles, you will get molar heat capacity. Okay. Now what is volumetric heat capacity? It measures heat capacity per volume. Now heat capacity is denoted by the letter capital letter C. It is given by limit delta T tending to 0, delta Q by delta T, where delta. Okay, study the definition for heat capacity, its mathematical representation, and the unit. These are all definitions that you can just go through. Heat capacities for homogeneous systems undergoing different thermodynamic process. First one is the at constant pressure, that is isobaric process. For that, dq is equal to du plus pdv, that is at constant pressure, heat supplied to the system will contribute to work done and change in internal energy. That is the first law of thermodynamics that we have already seen. So the heat capacity in that case will be called Cp, that is specific heat at a constant pressure, Cp. Now what happens to at a constant volume? V will be 0. So in dq is equal to du plus p dv, that since v is 0, dv is 0, so p dv term will be at 0. So dq will be equal to du, that is isochoric process, constant volume. No, in such process would imply that no work would be done. So the heat that we are supplying will contribute only to the change in internal energy. Okay, and here the specific heat at constant volume is denoted by Cv. Now the value of Cv is always less than the value of Cp. Now we know Cp minus Cv is equal to Nr, where now the ratio of that specific heat capacity at constant pressure to constant volume, that is Cp by Cv, is called gamma. Here n is the number of mole of gas, r is a universal gas constant, and gamma is the heat capacity ratio. Okay, we have got various relations relating the specific heat capacity Cp at constant pressure and specific heat capacity to Cp by Cv. Then Cv is equal to Nr by gamma minus 1. Cp is equal to gamma Nr by gamma minus 1. All these are certain relations. Now what happens at constant temperature, that is isothermal process? So when the temperature is constant, definitely there will not be any change in the energy. So infinite amount of heat is required to increase the temperature of the system. This will lead to infinite heat capacity of the system. Now what happens during the time of phase change or phase transition? In such cases, heat capacity of the system will be infinite. Why? Because heat is utilized in changing the state of matter. Okay, that is when a matter changes from one state to another, heat will be utilized. So definitely during a phase transition, heat capacity of a system will be infinite. Now this is an important derivation, that is you will be asked to derive the difference or show that the difference between specific heat capacity at constant pressure, that is Cp, and the specific heat capacity at constant volume Cv is equal to the universal gas constant R, that is Cp minus Cv equal to R. Prove this relation. That is a possible essay question. So let us begin. You know that the internal energy of a system is represented by the capital letter U. So let that U is a function of two variables, say volume and temperature T. Now using partial differentiative, U can be written as du, and now you are differentiating each of these with one variable. First you are differentiating with respect to volume keeping temperature constant, and then with the temperature keeping volume constant. So it will be dou u by dou t at constant volume dt plus dou u by dou v dv at constant t. We know that first law of thermodynamics is this one, that is dq is equal to du plus dw, but dw we know it is pdv. Now substituting from equation 1, that is equation 1 you are going to substitute. So in place of this dq you have to write dq will be equal to, okay, so dq will be equal to du. This dq is kept as such. This dq is kept as such. Now in place of du we have this relation, so you have to substitute that dou u by dou tv dt plus dou u by dou vt dv plus pdv. Pdv is kept as such, so that is equation 2. Now dividing throughout, that is dividing LHS and RHS with the dt. So this will be dq by dt. Here we are dividing with the dt, so it will become 1. Then again dv by dt, pdv by dt. Okay. Now here this term is kept as such, this is also kept as such. Here dv by dt is common, so it is taken out. Everything else is kept inside the bracket. Now if gas is heated under constant volume, we know dq by dt v at constant v equal to cv, that is the specific heat capacity under constant volume, and dv by dt will be equal to 0. So in place of this one, that is dq by dt, you can write it as cv. The rest will be kept as such, so it will be cv equal to, this one will be cv. Okay, this will be cv. Since this is 0, this particular term will become 0. So cv is equal to, what is remaining in equation 4 will be cv is equal to dou u by dou t at constant v. See, that is equation 5. Now when the gas is heated under constant pressure, in such cases, what will be dq by dt at constant p? It will be Cp. So from equation 4, you can write here, in place of this one, it will be Cp, and this will be kept as such if it is at constant pressure. So Cp is equal to dou u by dou Tv. See this one. Okay. Now taking, so already we have seen this is Cp, this is actually Cv, the rest is kept as such. Okay. Now taking Cv to this side, so it will be Cp minus Cv, everything, the rest will be kept as such. Now for an ideal gas during isothermal expansion or compression, no work is done, so heat transfer does not take place, so there is no change in internal energy. So here this term, that is dou u by dou t term, dou u by dou v at constant t, because use internal energy, that term including internal energy will be 0, so this will be 0. So what you are left with is Cp minus Cv is equal to dV by dt at constant pressure. Now we know that ideal gas equation PV equal to RT. Now you are going to differentiate it with respect to temperature. So first function into derivative second plus second function into derivative first, like that you have to do. So it will be the first function pressure, it is kept as this. Now the second function, you are differentiating with respect to temperature, so T will be 1, so you are left with the P dV by dt at constant pressure is equal to R. Now you have to substitute this P dV by dt at constant pressure is equal to R. Okay, so here in this equation we have already seen that this is equal to 0. Now we are left with the P dV by dt at constant pressure, and now we have found that it is equal to R. So you will read the equation as Cp minus Cv is equal to small letter R. That is equation 40. R is a gas constant for unit mass of gas. Cp and Cv are specific heat capacities. Now if Cp and Cv are molar heat capacities, then you will denote Cp minus Cv is equal to capital R, where R is a universal gas constant. That is equation 15. Now gas per unit mass, small letter r is equal to R by M, where M is the molar mass of gas. So here in today's class, this is a possible essay, that is derive the relation Cp minus Cv equal to R. So you can write it down, this is very simple. Then next is next everything is definition, so you have to study what is heat capacity. The other important one is state and explain first law of thermodynamics along with the required mathematical expression, that is very important. Then distinguish between heat and work, what are external work, internal work, etc., what is internal energy, etc. Okay, so please go through today's session. Thank you.